Hello everyone. Good evening, guys. Good evening, everyone. So, from my side, audio and video is clear. Tell me about your side as well. Tell me whether my audio and video is clear or not. Everyone. From my side, it's clear. I hope it is clear from your side as well. Okay. So I think we can continue now. So this class is again for 30 to 40 minutes, and we will try to cover the remaining part of the Nyquist plot, because till now we have understood what the Nyquist plot is and how we are going to use the Nyquist plot and how to check the encirclement. So for first 5-10 minutes I will revise it, and then I will tell you what is the direct method. You can skip the mapping part. You can skip the entire mapping of the right half contour, and it's a lengthy process. So what you can do is you can simplify this. There is a direct trick to solve the Nyquist plot. Okay, so that trick I will discuss in today's session, and let me revise a little bit, and then we will continue the trick part. Okay. So let me first cover the introduction part. So this is my introduction. My name is Asu Jangda. I teach almost every subject. You can start your preparation with me on BYJU'S exam prep platform. Okay, so you can join this platform, and let me tell you guys, there is a free free scholarship test on 23rd of July at 9 a.m. So you can register for this, and you can get scholarship up to 90%. If you perform well, you can get the scholarship. Okay, there is a free workshop on 25th of July at 7:30 p.m. This workshop will be taken by Dheeraj Sardana sir, and the title of the workshop will be In-Depth Preparation Strategy for GATE 2024. So you can join this workshop. You can recommend this workshop to your friends also, and you can get benefited. Okay, now it's time for Guru Dakshina, and Guru Dakshina is you have to subscribe our channel, you have to press the bell icon, and don't forget to like this session. Okay, so guys, in the previous class we have discussed about the application part, how the Nyquist concept is used to tell the stability of the closed loop system. So there were two important points. The poles of GSHS and the poles of 1 plus GSHS are same, and the zeros of 1 plus GSHS are actually the poles of closed loop system. So we are more interested in the zeros of 1 plus GSHS. They will tell you about the stability of the closed loop system. Okay, zeros of 1 plus GSHS are important for us. Okay, so that thing we have to see. Okay guys, so now you can see that this is the right half contour. So we have taken the right half contour, and the right half contour is in the S plane. You can see that this is the right half contour, and we can map this right half contour into GSHS, or you can map this right half contour into 1 plus GSHS. Now there are two different things. If you are mapping this right half contour into GSHS plane, and if you are looking the encirclement of origin, what does it mean? It means the number of encirclement will be equal to P minus Z. This P and this Z are poles and zeros of GSHS inside this S plane contour. Remember this point. If you are looking at the encirclement of origin in GSHS plane. Similarly, if you are mapping this S plane contour into 1 plus GSHS function, let's say there is a different function 1 plus GSHS. If you are mapping this right half contour into 1 plus GSHS, then you can say that and if you are looking the encirclement of origin, what does it mean? If you are mapping this entire right half S plane contour into 1 plus GSHS and looking the encirclement of origin, then that encirclement will be P minus Z again, or Z minus P. Now this P and Z are poles and zeros of 1 plus GSHS. Poles and zeros of 1 plus GSHS. Okay, so you have to be very clear. What is the meaning of P and what is the meaning of Z? Okay, so this P and Z are the poles and zeros of 1 plus GSHS inside this S plane contour, if you are mapping into 1 plus GSHS. Now what you can do is, because it's difficult to map into 1 plus, because first you have to calculate 1 plus GSHS, and then you have to check the encirclement of origin, and then only you can write like this. So to avoid this, what you can do is, you can map this S plane contour into GSHS and look at the encirclement of -1. This is the same thing that you are doing. You are mapping this S plane contour into 1 plus GSHS and looking the encirclement of origin. This is the same thing if you are doing the mapping of this S plane contour into GSHS plane and looking the encirclement of -1. You are looking the encirclement of -1. It is the same thing. Okay, so you have to be very clear about it. Okay, you have to be very clear about it. So what we are doing is, we are going to map this S plane contour into GSHS plane, and we'll look at the encirclement of -1. that encirclement will be P minus Z or Z minus P. Now this P and Z are the poles and zeros of 1 plus GSHS, because you are looking at the encirclement of minus 1. It means you have to check the poles and zeros of 1 plus GSHS inside this contour. Okay, and if you are mapping this S-plane contour into GSHS and looking the encirclement of origin, then the encirclement formula will be P minus Z or Z minus P. Now this P and Z are the poles and zeros of GSHS inside this S-plane contour. So you have to be very clear about it. It's very important, guys. Okay, you have to be very clear about it. Okay, now let's move ahead, and this I told you in the previous class, and I have taken one question also, and I have calculated the Z value. Okay, if you are looking the encirclement of minus 1 and calculate the value of Z, that Z will tell us about the closed loop poles. It will tell us about the stability of the closed loop system. Okay, so that was the case, and I hope you understood using this. Okay, so let's move ahead and let's look at this further. Let's move ahead. Now the next thing is, sometime what happens is GSHS is provided to you. Let's say GSHS is given to you. Let's say GSHS is given to you, and GSHS is given as some K naught into S minus Z1 or S plus Z1 divided by S plus P1 into S plus P2. Let's say this is my GSHS. This is my GSHS. So by looking the poles and zeros of GSHS, you can tell about the stability of GSHS only. Okay, you can tell us whether this open loop transfer function is stable or unstable. That you can check from the poles and the zeros of GSHS. Okay, you can check the poles and zeros of GSHS, and with the help of that, you can check the stability of GSHS only. But let's say you want to check the stability of closed loop system if GSHS is provided to you. And let's say you want to check the closed loop system stability. So what you can do is, if GSHS is provided, you can calculate characteristic equation. You can calculate characteristic equation. So characteristic equation will be S plus P1, S plus P2 plus K naught into S plus Z1. Okay, this is my characteristic equation. If you add 1 to it and take the LCM, then this is the characteristic equation. Now you can apply Routh. You can apply Routh here. Okay, using Routh you can check how many poles of this closed loop system are lying in the right half of the S-plane. It means if GSHS is provided, you don't need to go to Nyquist. Even you can calculate the number of encirclement. If GSHS is provided, then you can calculate the number of encirclement of origin as well as the number of encirclement of minus 1. How to do that? We know that the number of encirclement of origin, let's say, if you are mapping this S-plane contour into GSHS, okay, let's say this is my S-plane contour, this is my S-plane contour, and you are mapping this S-plane contour into GSHS, and you are checking the encirclement of origin, then the encirclement of origin will be P minus Z or Z minus P. Okay, now this P and Z are the poles and the zeros of GSHS inside this S-plane contour. Okay, that you need to check, because you are checking the encirclement of origin. If you are checking the encirclement of origin, then you have to check the poles and zeros of GSHS, and GSHS poles and zeros are visible to us, so we can directly tell what is the number of encirclement of origin. But let's say the number of encirclement of minus 1 is asked. Number of encirclement of minus 1 is asked, then it has to be either Z minus P or P minus Z. Whichever give you the positive answer, that you need to apply. Now what is this Z and what is this P? P is the number of pole of 1 plus GSHS inside this S-plane contour, and Z is the number of zeros of 1 plus GSHS inside this contour. Fine. Now the interesting thing is, we know that the pole of 1 plus GSHS and the pole of GSHS are same. So with the help of GSHS, you can calculate this P, pole of 1 plus GSHS. The question is how to calculate the zeros of 1 plus GSHS. The zeros of 1 plus GSHS in the right half contour can be calculated using Routh. Let's take an example. Let's say GSHS is given as 10 divided by S into s plus 1, s plus 2. And the question is, find number of right half poles of closed loop system. We have to find the number of right half poles of the closed loop system. How many poles of the closed loop system will lie in the right half of the S-plane? Okay, that we need to calculate. So how to calculate, guys? Using Routh. You can write the characteristic equation and you can find. So characteristic equation will be, so there is no need for Nyquist. Characteristic equation will be s into s plus 1 into s plus 2 plus 10. This is my characteristic equation. You can apply Routh and you can check how many poles, how many sign changes are there, and you will get the idea. So let's calculate that. So it will become s cube plus, tell me, the characteristic equation will be s cube plus 3s square, s cube plus 3s square plus 2s plus 10. This is equal to 0. This is my characteristic equation. And s cube, s square, s to the power 1, s to the power 0. So it will be 1 here, 2 here, and 3 and this 10. Okay. Now this point will be 6 minus 10 divided by, so minus 4 by 3. This is 0, this is 10. Okay. Now you can see the number of sign change are, there are 2 sign changes. It means 2 poles of the closed loop system are in the right half of the S-plane and the closed loop system is unstable. We know that. This is the question number 1. Now question number 2 is, find the number of encirclement of origin and minus 1. We have to find the number of encirclement of origin and minus 1 if S-plane contour, is mapped into GSHS. So what we are doing is we are mapping the S-plane contour into GSHS. After mapping, we have to check the number of encirclement of origin and the number of encirclement of minus 1. Okay. So it's very easy. Let's say you want to calculate the number of encirclement of origin. In GSHS plane, you want to check the number of encirclement of origin. So that number of encirclement will be P minus Z or Z minus P. Number of encirclement of origin will be either P minus Z or Z minus P. Number of encirclement of origin will be either P minus Z or Z minus P. Now, if you look at this carefully, the number of encirclement of origin in GSHS plane will be number of pole of GSHS inside S-plane contour in the right half S-plane contour. Obviously, the right half of S-plane. It should be right half. Right half. Okay. Now what you can do is n is equal to P minus Z or Z minus P. Now this P is the number of pole and Z is the number of zeros in the right half of the S-plane. Okay. This is my number of encirclement. Now you can directly see poles and zeros of GSHS in the right half of the S-plane. So you can see there is no pole in the right half of the S-plane. By default, I am taking this S-plane contour. I am taking this as S-plane contour. This pole is excluded. So you can see that there is no pole is inside this right half S-plane contour and there is no zeros inside this right half S-plane contour. So the number of encirclement will be 0. Number of encirclement of origin is 0. So directly you can find number of encirclement of origin if you are mapping this S-plane contour into GSHS. You can directly see that. Now, how to calculate the number of encirclement of minus 1? Now the number of encirclement of minus 1 will be equal to again P minus Z or Z minus P, whichever give you the positive answer that I should take. Now what is this P? P is the poles of 1 plus GSHS inside right half, and we know that the poles of 1 plus GSHS and the poles of GSHS are same. So there is no pole inside there is no pole of GSHS inside right half in the right half S-plane. Similarly, there is no pole of 1 plus GSHS inside right half plane because they are same. So P is 0. Now what is Z? Z is the number of zeros of 1 plus GSS inside right half. And we know that the zeros of 1 plus GSS are actually the poles of closed loop system. So you can see that the poles of closed loop system we have already calculated in the previous question. Poles of closed loop system, there are two poles of closed loop system are in the right half of the S-plane. It means there are two zeros of 1 plus GSS in the right half of the S-plane. So you can put that zero value here and you will get the number of encirclement of -1. I hope it is clear. So there is no need to draw the mapping. There is no need to check the mapping. You can directly use this Routh criteria to find the number of encirclement of -1 or number of encirclement of 0. But you have to be very careful. In which function you are mapping, that should be known to you. And the S-plane contour should be known to you, because sometimes what happens is the contour is like this. They include the pole, origin pole, okay? They include the origin pole, then things will change. This time you will find that the number of encirclement of origin will be there. It will be non-zero, and the number of encirclement of -1 will also be there, okay? So you have to calculate, you have to be very careful. You have to check S-plane contour and in which function you are mapping and which point you are looking. Are you looking the encirclement of, are you looking for encirclement of origin or encirclement of -1? That is important, okay? That point should be clear to you. I hope it is clear, and I hope you understood how to apply this concept without doing mapping. Now there is one more trick. There is one more trick. And that trick is using 511. Okay, using 511. Okay, let me tell you guys. There is one concept, 511. 511 is Z minus P minus PW by 2 into 180. Into 180. Okay, this is my 511. Now this is, maybe it is new to you, but again this concept is very important. If you know how to calculate 511, then also you can comment on the stability of the closed loop system. Now what is this 511? Let me tell you guys. Let me tell you what is this 511. Let's say there is some GSHS. Some GSHS is provided to you. And that GSHS is maybe some 10 divided by S plus 1, S plus 2, and S plus 5. Let's say this is my GSHS. And you have S-plane contour. You have this S-plane contour. You have this S-plane contour. This is my S-plane contour. Okay, we have this S-plane contour. Fine. Now what we want to do is we want to check the closed loop system stability, whether the closed loop system is stable or not. Now you can see, if I map this part only, this J omega part, then the contour will look like this. Let me map the J omega part only. If you are mapping the J omega part only, then it will look like this. Okay, it will look like this. Let's take it maybe 1000 for the time. Just take 1000. Okay, so it will start from 10 and it will go like this. Okay, or maybe it will start from 100, I suppose. Okay, it will start from 100 and it will go like this. So this is the, you can say this is the mapping of this J omega axis in the GSHS plane. Now how to calculate this 511? First of all, let's try to understand. First of all, you have to check what is this point and whether -1 is inside this or outside this. You have to check. Let's say for the time being, let's say -1 is inside this. -1 is inside this. Now this 511 is angle with respect to -1. If omega varies from infinity to 0, if omega varies from infinity to 0, then what is the net angle subtended here with respect to -1? Net angle traversed with respect to -1. What does it mean? Okay, let me tell you what does it mean. First of all, you have to move from infinity to 0. Okay, here omega tends to infinity and here omega is equal to 0. So you have to move from infinity to 0. Fine. Now what you need to do is you have to check phi 11. What is the net angle subtended? So the net angle subtended is, so you have to start from here. With respect to this -1, you can see that the net angle subtended is this. So you are rotating in this direction, guys. You are rotating in this direction. It means you are rotating clockwise. So how much net angle is traversed in clockwise direction? Oh, sorry, you are moving anti-clockwise. You can see that. You are moving anti-clockwise. In anti-clockwise, the angle has to be positive. It means this phi 11, it will be how much angle you have rotated with respect to -1. You have started from 0 and then pi and then one more pi. It means 360. You have rotated by 360 degree. You are moving anti-clockwise angle will be positive. Okay, I hope it is clear. So this is my phi 11. So first of all, you should understand how to check phi 11. Let's say -1 is outside. Maybe I can change this k value and let's say -1 is outside this. Okay, in that case, what is phi 11? Let's see what is phi 11. Okay, let's say it is like this. Okay, -1 is somewhere here. Now if you look at the net angle subtended with respect to this -1, it will be like this. It will go upside like this and then go down. So from this point to this point, net angle subtended is 0 because you have gone up and then gone down. Net angle subtended is 0 and then you are going downward and then again you are going upward. It means ultimately you have started from 0 degree, you go upside, you go down. Net angle subtended is 0, then you go downward and then again you go up. Again net angle subtended is 0. It means with respect to -1, net angle subtended is 0 in this case. So you should know how to find phi 11. While calculating phi 11, you should move from infinity to 0. Okay, you should move from infinity to 0. Let's say the polar plot is like this. Let me give you one more case. Let's say the polar plot is like this. This is the polar plot. Okay, and you are moving from infinity to 0. So arrow is in this direction. Okay, you are moving like this. And let's assume that -1 is somewhere here. This is -1. Now if you are moving like this, then you can see that the net angle subtended is this. This is the net angle subtended. So net angle subtended is, again you are moving in anti-clockwise direction, and net angle subtended, because this point is very far away, so a straight line will meet that. So the net angle subtended is 270. Okay, it's 270. So phi 11 is 270. Okay, you have to be very clear how to calculate phi 11. Okay, that is important, guys. So first you should know how to calculate this phi 11. And this phi 11 is Z minus P minus PW into 180. Z is number of poles of closed loop system. Z is the number of zeros of 1 plus GSS, you can say. P is the poles in the right half of the S-plane. PW is the poles on the imaginary axis. Okay, PW is poles of GSHS, on imaginary axis. Okay, and P is the poles of GSHS, inside S-plane contour, inside a right half S-plane contour, Okay, this is my P. P is the poles of GSS inside right half S-plane contour. And Z we need to calculate. So first we need to find phi 11 using this polar plot. You don't need to plot the entire Nyquist, okay? Only the polar plot is required. So what you need to do is you need to draw the polar plot. Using that polar plot with respect to -1, calculate phi 11. Calculate the poles of GSS in the S-plane contour. Okay. Calculate the number of pole of GSS on the imaginary axis, and you can put those values here and calculate the Z value. The Z is the zeros of 1 plus GSS. It means the poles of the closed loop system. And using this formula, you can calculate whether the closed loop system is stable or unstable. Using this Z value, you can calculate that. Let's take an example. Let's say one graph is given to you. Let's take an example. Wait. Let's say some polar plot is given to you. And the polar plot is like this. Let's say this is the polar plot. Okay, polar plot is like this. Omega equal to 0, omega tends to infinity. This point is minus k by, let's say minus k by 10. This is minus k by 5. And this is minus k by 2. Okay. So these are the points which are given to us. Okay. Only polar plot is provided to us. Given that one pole of GSHS lies on imaginary axis. It is given that one pole lies on the imaginary axis. One pole of GSS lies on the imaginary axis. Okay, it is mentioned. Find the range of K. Find the range of K for stability of closed loop system. For the stability of closed loop system, we need to find the range of K. Given that the open loop system is stable, one pole is on imaginary axis, so it is marginally stable. Open loop system is marginally stable. Open loop system is marginally stable. It is provided to you. Marginally stable. It means one pole lies on the imaginary axis, remaining pole lies on the left half of the S-plane. Okay. So open loop system is marginally stable. It is provided to you, and we need to find the range of K in which the closed loop system is stable. The polar plot is provided to you. Now it's simple. Using this phi 11 concept, you can check that. How to do that? First of all, let's assume that -1 is somewhere here. How can you assume -1 here? If I take K to be greater than 10, if K is greater than 10, let's say 20, so this point will become -2, and -1 will become here, minus will come here. Okay, this is my -1 point, and this is my -1 point, and the polar plot will go like this. And the polar plot will go like this because I am moving from infinity to 0. Now I have to calculate phi 11. So I am writing for K greater than 10. First, I am looking for K greater than 10. Okay. Now, with respect to this point, what is phi 11? You have to check. So you can see that this point is moving like this. Up to this point, the net angle traversed is anti-clockwise. So it is positive and it is 180. Now again, you have to go downward. Okay, now you have to go downward and then you have to come again upward. So from this point to this point, there is no angle traverse because you have gone downward and then upward. Net angle traverse is 0. So only 180 degrees this. From this point to this point, 180 degrees phi 11. Okay, 180 degrees phi. From this point to this point, 0 degree. Now from this point to this point, again you have moved up. You have moved up and then down. And then down. Okay. You have moved up and then down. So net angle traversed is again 0. Net angle traversed is again 0. Then after you have moved downward like this. You have moved downward, okay? You have moved downward like this, okay? So the net angle traversed is again anti-clockwise and it is 90 degree. Net angle traversed is again, okay? So net phi 11 is 270 degree. So let's put it here. 270 is equal to Z minus P. P is 0 minus PW by 2. PW is 1. One pole on the imaginary axis, it is provided, into 180. Okay. Now from here you can see that this is gone and it will be 3 by 2 is equal to Z minus half. So Z came out to be 2. It means the system is unstable. For this value of K, the system is unstable. Unstable. System is unstable. Okay. So if minus 1 lies here, it means if K is greater than 10, the system is unstable. Now let's take the second case. In the second case, what I'm doing is, let me draw the polar plot again. So this was the polar plot. Wait, let me draw it again. So this is the polar plot. Now I'm assuming that minus 1 is lying here. Okay. Minus 1 is, this point is minus K by 10. This point was minus K by 5. Now what I'm doing is I'm assuming this. So the minus 1 point will lie in between these 2 points if K is greater than 5 and less than 10. Okay, you can see that. If K is greater than 5, less than 10. Let's say K is 8. If K is 8, this point will be 0.8, minus 0.8, and this point will be minus 1.6. So minus 1 will be in between this. Okay, I hope it is clear. Now let's see whether it is stable or unstable. Okay, again you have to calculate phi 11 and you have to move in this direction. So let's calculate that. So first of all, what you are doing is you are starting from this point and you are going up to this point. So with respect to this minus 1, you are moving like this. You are going upside and then you are coming downside. So net angle traverse from this point to this point is 0. Going up and you going down. So up to this point, net angle traverse is 0. Now what you have done is you are starting from this point to this point. So you are going like this. You are going like this. Now tell me, what is the net angle traversed? You are coming from this side to this side. It means you are moving clockwise this time. So net angle traversed from this point to this point is minus 180. Now again from this point to this point, the net angle traversed is you are moving upside from with respect to minus 1 I am looking, and then you are coming down. Okay, so net angle traverse is 0. From this point to this point, net angle traverse is 0 because you are moving up, and then you are coming down. Net angle traverse is 0. Now from this point onward, you are going downward like this. You are going downward like this. Okay, you are going downward like this, and ultimately the net angle traverse is again in anti-clockwise. You can see that it is anti-clockwise, and the net angle traverse from this point to this point is 90 degree. So it is plus 90 since it is anti-clockwise. Okay, so this was clockwise and this was anti-clockwise. From this point onward, anti-clockwise. So net phi 11 is minus 90. Phi 11 is minus 90. Now you can put minus 90 is equal to Z minus P minus PW by 2 into 180. So Z came out to be 0. So this case is stable. In this range, the system is stable. In this range, the system is stable. Okay, I hope you find it. Now let's come to the next. Next is I am taking K. The minus 1 is between this point. Okay, let's come to the next case also. Okay, so this is the polar plot we have. Okay, and I'm assuming that minus 1 is lying at this point. Okay, so this was 0, this was minus K by 10, this was minus K by 5, and this is minus K by 2. It means what I'm assuming is I'm assuming that K is greater than 2, less than 5. Okay, previously it was between 5 and 10, now it is 2 and 5. If K is between this range, then minus 1 will lie here. And look at the phi 1 1 now. From this point to this point, net angle traverse is 0 because you have traveled upward and then downward. So net angle traverse is 0. Next, from this point to this point, again net angle traverse is 0 because you are going downward and then you are going upward. You can see that you are going like this. Okay, and again you are going like you came like this. So it means net angle traverse is 0. Now from this point to this point, net angle traverse is anti-clockwise and it is 180 degree. Okay, it is 180 degree. I hope it is clear. And then you are going down again. So further 90 degree. So again it is 270. And we have seen that if phi 1 1 is 270, it was unstable. So again it is unstable. Again in this range it is unstable. Now there is one more range, k less than 2. Okay, for k less than 2 it will look like this. For k less than 2 the graph will look like this. Let me draw the graph. Okay, so -1 will lie here. This point is minus k by 2. This point is minus k by 5 and this point is minus k by 10. This point is 0. Okay, now it is like this. So if you look at the phi 1 1, then from this point to this point phi 1 1 is 0, from this point to this point phi 1 1 is 0, from this point to this point phi 1 1 is 0, and from this point onward it will move like this. So the phi 1 1 will be again clockwise. So this time phi 1 1 came out to be minus 90, and for minus 90 you will see that system is stable. You have already seen that. Okay, so for k less than 2, greater than 0 obviously because I am taking k positive. So if I am taking k greater than 0, less than 2, again it's stable. So using phi 1 1, using this phi 1 1 concept, if you know how many poles are on the imaginary axis and how many poles of GSHS are in the S-plane contour, inside this S-plane contour, then you can calculate the Z value. But for that you have to get the phi 1 1. It means there is no need for entire Nyquist plot. Only the polar plot is sufficient. Only this side of mapping is sufficient. Using that polar plot, you can calculate phi 1 1 and you can check whether the closed loop system is stable or unstable. Okay, I hope it is clear, guys. In the next class, we will take some good questions on this and we will try to solve some questions. Okay, so I hope you enjoyed today's session, guys, and I hope you have learned something new in today's session. I have told you about phi 1 1 concept, and there is one more Routh criteria. Okay, how to use Routh without using the Nyquist contour. You can use Routh also. So those two things I have told you. So that's all for today's session, guys. I hope you enjoyed. So don't forget to subscribe our channel and like this session and share this session with your friends also. Press the bell icon so that you get the notification. And there is one important thing. We have our mobile app. Go to the Google Play Store, install our mobile app, and you can also watch free classes on mobile app there. Okay, so that's all for today's session, guys. I hope you enjoyed. So thank you and take care. Bye.